Hi, Austin. Sorry for the delay, but I'm gonna do a little video explanation of that problem you sent me. It doesn't tell me exactly which problem it is in your homework, but either the top or left corner, the top left or top right corner, it says 7.4.29. But you'll probably recognize it when I write out the problem. So it starts off asking us to find the integral of x squared divided by the square root of 121 minus x squared. So because I see that difference of squares in the denominator, and u substitution will not work because our x's have the same power, this is a good candidate for trig substitution. So anytime we see subtraction, we're going to set up our triangle so that the first piece is the square of the hypotenuse, and the second piece is the square of our opposite leg. And then Pythagorean theorem on this triangle tells me that this adjacent side will be the whole square root expression. So right now we have the square root expression in our fraction, but we would prefer to use some simpler terms. So if you look at the other two sides of our triangle, they are much simpler. So based on where I drew my theta, x is the opposite side, 11 is the hypotenuse, and we need to figure out which trig function uses opposite and hypotenuse, and that's sine. So sine theta is x over 11, and I'm going to multiply the 11 over, and that gives us our substitution for x. X is going to get replaced with 11 sine theta. We also need to replace the dx, so I'll take the derivative of both sides of the equation, and I get dx equals 11 cosine theta d theta. And I'm going to go ahead and plug all of this stuff in. Everywhere I see an x, I'm going to put 11 sine theta instead. And then at the end where I have my dx, I'm going to put 11 cosine theta d theta. So this integral turns into 11 sine theta, all squared on the top. And then in the bottom, we've got 121 minus 11 sine theta squared in the bottom. And then dx is 11 cosine theta d theta. There's a lot of simplifying we can do here, but we are guaranteed that this piece will simplify because we set up this triangle specifically to match up with that difference of squares piece. So we will definitely be able to simplify at least that part. So you can always start with that simplification. I'm going to go ahead and take this 11 cosine theta and multiply it into the top. So we have 121, sine squared theta, and then 11 cosine theta in our numerator. Now in the bottom, first we need to square. And when we do, you see that 121 comes up twice in there. So what we're going to do with that is we're going to factor the 121 out. And right now I'm just going to work with the square root piece. So just this part. We can think of that as 121 times 1 minus sine squared theta, if we were to factor the 121 out. And then 1 minus sine squared theta is equal to cosine squared theta from a Pythagorean identity. So this is the stuff that we have under our square roots. So now, written as 121 cosine squared theta, because there's no addition or subtraction, we're allowed to just take the square root of both of those pieces and get 11 cosine theta in the denominator. So I'm going to go back to my integral now and replace my denominator. So our numerator is still the same. We haven't done anything with that yet. And after simplifying, our denominator is simplified all the way down to 11 cosine theta. And we can do some simplifying here because we've got 11 cosine theta in the top and the bottom. So they completely cancel out. And it just leaves us having to integrate 121 sine squared theta. Well, in section 3, we talked about some different strategies for integrating trigonometry, and with sines and cosines, if you don't have an odd power to work with, then you're going to have to use a power reducing formula. So I'm going to pull the 121 out front. It's just a coefficient. It's going to carry along from step to step. Sine squared theta is equivalent to 1 minus cosine 2 theta all over 2. That is a trig identity. You most likely did not learn that specific trig identity in trig class, but all it is, let me write it here, sine squared theta equals 1 minus cosine 2 theta over 2. All this is the cosine double angle identity that got solved for the sine squared. So this is really just a double angle identity where the terms got rearranged a bit. So that divide by 2, I'm going to go ahead and just move it out front with my 121. It's a coefficient. It's not going to affect how we take our derivative or antiderivative. And that makes it look a little bit easier because now we don't have to worry about fractions. So the antiderivative, let me add another page here. But the antiderivative for 1 with respect to theta is just theta. And then the antiderivative for cosine 2 theta, you might want to write out a little u substitution for that because this is technically a composite function with an inside and an outside. So we're going to say u is 2 theta, du is 2d theta, which means in order to do this replacement for d theta, we're going to have an extra 1/2 coefficient in our problem. So what we have now from our last page, we had a 121 over 2 integral of 1 minus cosine 2 theta. Now when you do the substitution, we don't need it to integrate the 1. You only need it to integrate the cosine 2 theta. So you could break this into 2 pieces if you wanted to. We need the integral of 1 with respect to theta, and then the integral of cosine 2 theta with respect to theta. And only the second part requires that u substitution. So if we use that u substitution we had on the last page, we could replace the 2 theta with a u as long as we brought an extra 1/2 coefficient into the problem. So I've got 121 halves. The antiderivative of 1 with respect to theta is theta. And then the antiderivative for cosine is sine. So this is 121 halves theta minus 121 fourths sine, and we said u was 2 theta plus c. And now our last step is to just get this back in terms of x. And we've got 2 special cases in this one that make it a little bit more difficult. We've got a theta with no trig function attached, and then we have a sine 2 theta, and our triangle is not set up to tell us the trig values for an angle of 2 theta. It's set up to tell us trig values for an angle of theta. So we need to convert 120 halves theta minus 121 fourths sine 2 theta back to x. And our original triangle that we drew right at the beginning to figure out our substitution had 11 on the hypotenuse, x on the opposite side, and then our big square root piece on the adjacent side. We also said that the way we started our substitution was by saying sine theta is x over 11. And this is going to help us with this first substitution we have to do, this first conversion. So if sine theta is x over 11, that means theta is sine inverse of x over 11. So that's how we're going to replace the theta. And I've got one mistake here. Let me fix it real quick. We've got an angle of 2 theta here. So for the sine 2 theta, we're going to have to use a trig identity to write that out in terms of just regular theta. So far we've got 121 halves sine inverse of x over 11. That's how we're going to convert back the theta. The sine 2 theta, that's a double angle identity that says sine 2 theta is equal to 2 times sine theta times cosine theta. So now that it's back in terms of theta, we can use our triangle. If we bring that 2 out front, it's going to turn into 121 halves. Sine theta on this triangle is sine is opposite over hypotenuse, so x over 11. And then cosine is adjacent over hypotenuse. So the square root of 121 minus x squared over 11. And there's just a little bit of simplifying we can do because 11 times 11 in the bottom is 121. So they can cancel out. And I would say the final answer in the most simplified form is 121 halves sine inverse of x over 11 minus 1 half. We still have that 2 there in the bottom. And then we've got those numerators in the fraction. So x and square root of 121 minus x squared plus c.